Okay, everyone, so let's do an example. So as you can see here, we have a ball, it's in a slot, and this whole plate is going to be spinning at an angle, or spinning the entire time. Now we know at any instant its angular position is theta. Oh my goodness, there's a t in that equation, which means, guess what, we can take time derivatives of it. And the ball rolls outward, so that its position is going to be 0.1 t cubed. We know a whole lot for here. So it wants us to know the magnitude of velocity and acceleration of the ball when t equals 1.5 seconds. Spoiler, lots of time derivatives and lots of plugging into those earlier equations. What was your plan? Well, use a polar coordinate system and all of our related kinematic equations. Now, I'm going to pause here, give you a few minutes to try this out on your own. Plug all in, take your time derivatives, plug in the numbers, and see what pops out and see if you get it correct. And I'll see you all soon. So 3, 2, 1. You paused, you did it, you rocked it, or you didn't, and now you're back. So let's try it out together. Now we have r equals 0.1 t cubed. We take a time derivative, t squared. We take another time derivative, 0.6 t. Same for this one. We keep on taking time derivatives, and we get down to here. These time derivatives are fairly simple. Just be very careful that you do them correctly. Now, as soon as we have all of our derivatives taken, we just plug in our time of 1.5 seconds, and we get all these numbers. There are so many numbers here, and these are not the answers. This is just a start. Also, when you see radians, if you're worried about how it works in an equation, it just disappears. Radian is the same as strains if you're in my solid mechanics class. Radian isn't really a dimension. It's more or less letting you know that this is an angle, but it does not actually work as a dimension. You always multiply radians by radius, and then it disappears and turns into the units of the radius. Whatever radius you multiply by, that becomes its units. So we substitute all this into our equation for velocity, which is r dot and r theta dot. Well, we get our two components for velocity, which is 0.675 and 2.480. And if we square each of those components, add them together, and then take the square root, well, it's 2.57 meters per second. That would be our max. So as you can see right here, I didn't really have to do much. Once I get these numbers, I just plug it all in. So for any cylindrical coordinates problem or any polar coordinates problem, it's usually good to just go ahead and get all of these calculated to help yourself out. Now acceleration, once again, I just plug in everything I know, being very careful with my calculator. Calculator errors are terrible. Doom. So be careful. Then you plug it in here and you get our acceleration with the radial component and the transverse component, or the theta component. You can call it what you want. I won't judge you because I go back and forth. That'll be 20.4 meters per second square. So that is this example. That is this problem. Now, it's your first time doing it. To me, it wasn't that straightforward this time. Just remember, though, it's those time derivatives. That's what's going on here. Time derivatives over and over and over again. So make sure that you are practicing the time derivatives and practicing with your integrals. You don't do very difficult ones. I won't be asking you to do U substitution in this class or anything too crazy. However, you got to practice, make sure that you can do them fairly quickly just so you get the problems done in time. If you're having trouble with those derivatives or integrals, let me know. Send me an email, and I can send you some resources to help you with that. Thanks for listening. I'll see you all next time. Bye-bye.